Welcome back to the Love Talk seminar with me, Tracy Holbrook, your organic instructor and your personal relationship counselor. And in today's video, in this seminar, and I'll send you a bill and an invoice a little bit later, we need to talk about substitution reactions. All right. And we said we're going to have SN1 or we're going to have SN2. And we talked a little bit in layman's terms about the differences in substitution reactions. All right. So here, let's be a little bit more specific. Here's option number one. We're going to have a nucleophile. We now know what that is. We just reviewed it. And it's going to be attracted to a partially positive carbon. We talked about that as well. This partially charged carbon, folks, keep in mind we called that an electrophile, right? Electrophile, electron loving. It's electron loving because it has a positive charge right now. So it's going to form a new bond with carbon while carbon releases the halogen. So we have a special term for this. This whole forming a new bond and ending the other bond. We'll talk about details a little bit later, but this is going to be called a heterolytic cleavage. All right, so there's option number one. Option number two, a little bit more sciencey. The halogen cleaves from the carbon. And this is forming a carbocation. A full-blown carbocation, folks. When it forms that carbocation, that's when the nucleophile is attracted to the carbon. These are called SN2 and SN1. SN2's up here. Carbon's a cheater. Carbon has a new bond. Carbon looks at the old bond with the halogen, decides to get rid of the ugly one, kicks it to the curb. Carbon number two, or option number two, is an SN1. The halogen leaves first, carbon becomes single, fully single, and it forms a full carbocation. And then the nucleophile goes in and forms a new relationship. So with that said, here on the screen, what you're seeing are SN2 reactions. They have what we call very good leaving groups. So up here at the top, you're seeing the polarity difference between the carbon and the halogen. The halogen's more electronegative. The halogen has this squiggly minus. The carbon, because of that, is more positive. There's a charge distribution, and that is a partial positive or squiggly positive charge. This is a polar bond. And this halogen, keep in mind, can represent any of these. Now, they don't even list iodine, do they? No, they don't even list iodine for SN2 reactions. Why? It's ugly, honey. It's ugly. All right, down below, how do alkyl halides react? Well, this is the mechanism that we're going to be doing over and over and over. So with SN2, we have this nucleophile that I can also represent with a Y. You pick it. It means the same thing in the world of organic. Nucleophile, of course, NU, or the Y. So this nucleophile comes in and it says, hey, hubba hubba. And that carbon says, oh, okay. And it actually looks at both the halogen and this new group at the same time. It forms this new bond, and it's a cheater. SN2s, folks, are the cheaters. So carbon grabs onto this halogen, carbon grabs onto this nucleophile, and it says, which one do I like the best? It could take me a couple of days, or it could take me a couple of years to figure it out. You don't want that. Molecules don't want that either, really, but some of them are okay with it. Don't ask me. So this nucleophile comes in, and poof, off goes the ugly little halogen. Carbon's almost always going to get rid of the halogens. They're always ugly to it. Everything is so much prettier than the halogens. So that chlorine and the bromine typically going to get kicked every single time, which makes these the easiest types of substitutions, which also makes it why we focus on these so much. So this is our substitution product that we have created now. This new group is now attached at the location of where the halogen was. Well, what if carbon's not a cheater? Well, here's that example. Here we have carbon associated in a bond with a halogen. And again, it's a polar bond. This is electronegative. It's more negative because of that reason that carbon is partially positive, and this halogen decides to leave first. Now what we've created is a full carbocation. And that carbocation is going to give the molecule enough time to kind of get its act together before getting into a new relationship. So if that means that the carbocation needs to rearrange and go to a better place, then right now is the time that this molecule is going to do it. Once the carbocation has found its perfect spot, that is when the nucleophile will come in and say, hey, hubba hubba. And carbon says, okay, come on. And that's what happens. They fall madly in love until something else comes along that catches that carbon's eye. That is another substitution product. We've had a halogen, and that halogen now gets substituted and replaced with another group. That's exactly what happened here. We had a halogen. That halogen has now been replaced, and it's now substituted for another group. It's the mechanism that makes them different. Does carbon cheat and sees the two at the same time? Or does carbon have a heart, morals, and decides to say, you got to go, halogen leaves, carbocation forms, single, and then the new group comes in at that spot. So substitution, nucleophilic. That is what this lecture is all about. The issue here, though, that most people have, and this is always the problem, especially in the beginning, is which. Just like with experience, I think that you could probably go into somewhere, some type of social gathering, and be able to pick out, God, he's a cheater. Stay away from her. She's a cheater. I think you probably have been at that point at some time in your life. If not, it will come. And you probably will say that by just looking at how they're acting and how they're behaving, and you're probably stereotypical. Or you're saying it from experience because it's happened to you before. And we need experience with this. We need experience working these problems, and we need experience being able to figure out how these carbons are going to start behaving. Are they going to be cheaters, or are they going to be the good ones? So it's going to take some time. And there's a couple of things that we need to do in order to figure out which one goes first. Which one is preferred? Is this carbon going to be a cheater, yes or no? All right, so here are the 4 things that we can do in order to help make this decision. Number 1, we have to look at the structure of the alkyl halide. Okay, so what type of carbon is there? Primary, secondary, tertiary. What type of halogen is there, right? Those are the things that we're going to have to look at structure-wise. Number 2, the reactivity of the nucleophile is also going to be important. How pretty is pretty? You know, I mean, is this like Miss America of the bar? I mean, is everyone's eyes on that nucleophile? If so, then that reactivity is going to be very, very high. But if it's just a you know, let's say that you've got an 8 right now as a partner and this other one walks in, it's like 8.5. I mean, is that really going to be justification to go out and end a relationship that you're in right now? Maybe not. That's going to take slower. It's going to take a longer process if it's going to happen at all. And that's what we see with the reactivity of the nucleophile. We just got to be able to determine how pretty is pretty. Number 3, we also have to look at the concentration of the nucleophile. In other words, when they show up to the party, are they the center of attention? Is there just so much attention brought onto that nucleophile that everything just stops, everybody pays attention to that person, and then everybody wants into that person's pants? I mean, that's exactly what's going to go on here with the substitution reactions. And number 4, we have to talk about the solvent of the reaction. So is this taking place at a wedding? Is this taking place at a bar? Is this taking place at a work function? That's the solvent. That's the environment. And as you can imagine, these cheaters will have different affinities to cheat depending on what type of environment they're in. And if you're at a bar and you're liquored up, you're probably more prone to go out and cheat. That's just the way it is. If you're at a work function where everyone's trying to behave and be all prim and proper, maybe not so much. That's the solvent of the reaction. So these are the 4 components that we have to go through. We have to talk about them. We have to look at them, because this will help us determine whether it is SN1 or whether a SN2 is going to happen. Let's talk about SN2 first. With SN2, the rate depends on the concentration of the alkyl halide and the concentration of the nucleophile. Notice I wrote both. Both concentrations are important. The rate, which is the speed, that's kinetics. The rate that this happens depends on the concentration of the halide and the concentration of the nucleophile. Both concentrations are important, therefore SN2. That's 2 NOD, first order, second order. That's the definition of second order. For those of you that didn't remember that from general chemistry, not a problem. I got you back. Bulky molecules. Well, we've got an issue here. Bulky molecules slow down the reaction. We'll see a few of these examples. Think of this as friends going to the club to allow this to happen or to prevent this from happening. That's what these bulky molecules are going to start doing. Next, for an SN2 reaction, we also have to keep in mind that the attacking group, you know, that other one that carbon's got his eye on, the attack is going to happen on the opposite side of the molecule. Why do I bring this up? Folks, this is stereochemistry right here. When we start adding things on the back side, then we start flipping the R's and the S's with each other. That's one of the reasons that we talk about it. In other words, what I'm saying here is that if carbon's going to cheat, this cheating group cannot come to the front door. the neighbors are going to see it. This cheating group has to be snuck in from the back door. Just come around to the yard and the back side of the house. The door's unlocked. Just come on in. That's what this carbon says. So we get a rear attack from the back door of the home of the cheating carbon, while maybe the relationship group is leaving out of the front door at the same time. Can you imagine? I mean, this is like a movie stuff, right? Well, we've got a special term for this. This is called a backside attack. And you can kind of see why. It's coming through the back door. It's flipping everything around as far as stereochemistry goes, because carbon has to see both at the same time, and they just can't allow both of them to come through the front door. He doesn't want both of them to realize that they're there at that point. So he's going to sneakingly do this and see both at the same time. While he stays at the house, the other one leaves, the other one comes through the back door at the same time. This reaction is also called a concerted reaction. This is something that we have talked about before. We've mentioned it before. And concerted means one step. It all happens in one step. No intermediates are going to be formed in an SN2 reaction. So generally speaking, folks, this is what an SN2 is. The rate or the speed depends on the concentration of both species. We don't really like to use bulky molecules in SN2. It slows everything down tremendously sometimes. When things do react, well, it comes on the opposite direction. So stereochemistry gets flipped, if that is a thing that we need to worry about. And then this mechanism happens all at once. It's a concerted reaction, and that's what that means. So now let me give you an example. Let's say that we have a very simple alkyl halide, methyl bromide. Methyl bromide is here. Methyl bromide has fell in love. They're high school sweethearts. Oh, bromine, I love you so much. And there's your molecule. And everything goes good for a while. Methyl group and bromine seem to get along. No problems. A little bit of bickering, a little bit of fighting, but that's normal in all relationships, isn't it? And then methyl bromide decide to go out to the club one night or to the local bar just to have a few drinks, kind of like a date night. They haven't done that in a while. Things are getting kind of stagnant. So they decide to go out on a Friday evening, have a few drinks at a bar, kick back, relax, and then lo and behold, boing, here we get an OH group that comes in. And that carbon is going to look at that OH and say, holy smoke. What am I doing with this toothless, warty bromine? And when I could have something like that OH group right there. Oh. Well, if a cheater happens, this carbon will hold on to the bromine and pretend and sweet talk love nothings in its ear the entire time that they're together. But at the same time, this carbon is open to that OH group and kind of testing the waters out a little bit. So this nucleophile, like always, we start a curvy arrow at it, comes in and says, hey, carbon, hey, good looking, what are you doing? And this carbon accepts it. This carbon begins to cheat. And the carbon sees the bromine and the OH at the same time. Carbon then makes the decision, yep, OH is the one for me. And carbon looks at the bromine and says, bromine, you got to go. I'm tired of it. I know that we've been together for a while, but you know what? I'm superficial. It's all about the outside. I like OH a little bit better because it's prettier, and I'm sorry, but you're just ugly. Bye-bye. Oh, boo-hoo. Poor little bromine. So bromine goes off on its own. It carries with it those electrons, so it carries with it a negative charge at this point. That's why the arrow started at the bond and was pushed toward the bromine. And then now what we have is a CH3OH group. That OH group has came in and substituted for the bromine. Well, this is happening all in one step. It's concerted. This is an SN2 reaction. Notice the bromine left at the same time that the OH came in. Why does this happen? Again, it's due to polarity. The bromine is electronegative, so it's partially negative anyway, and that made this carbon partially positive, which is why that OH was attracted to it to begin with. So this is taking methyl bromide, reacting it with the hydroxide ion, and that creates methyl alcohol and the bromide ion. See how sneaky I did that? This is happening in a concerted reaction with an SN2 mechanism. That's what goes on. So now methyl alcohol, or methanol, has now went off, created a brand new relationship, and they're going to go start their life together. And poor little bromine is out on its own, but it's okay. It was electronegative anyway. It kind of didn't want to be in that relationship because it was electronegative, and it really just was sucking the maybe money from the carbon, and it was like, just give me the checkbook and I'll go. And that's exactly what bromine did. Bromine took the money and ran. And it's okay. Bromine can take care of himself or herself, however you view these. The CH3OH group, new relationship, carbon's happy, OH is happy, and then away they go. Happy little life. It's like a fairy tale ending. If I wanted to talk about stereochemistry, I could. However, in this case, it didn't matter. Well, why, you say? Well, take a look at this carbon. This is a carbon with a hydrogen, a hydrogen, a hydrogen, and a bromine, right? 4 bonds. Bromine leaves and OH comes in. Folks, this is not a chiral carbon, right? The reason is there's no 4 different groups attached to that carbon. So the whole term of R and S does not apply here. This did not matter. Now, if we did have a chiral carbon, we could assign R and S to those, and we have to keep in mind that SN2 is a backside attack. So if this was a R molecule in the beginning, it would end up with a S molecule after the reaction takes place, or vice versa. All about the stereochemistry, if it goes that route. Sometimes they're good and they just don't want to do it. They feel like they're wrapping too many things up all at one time. But look at what we've had here. Methyl bromide, methyl alcohol. You know, this was like lecture module 2 stuff when we learned about alkanes. The OH groups. The OH group serving as a nucleophile and an electrophile. This was kind of at the beginning of the reactions that we started to talk about with alkenes. So this was like lecture module 3 stuff, right? And then they're going to bring in chirality of R and S, which is what we recently have talked about in like lecture module 6 or 7. So once again, this whole thing is cumulative. I keep saying it over and over, but I feel like I have to keep proving my point. So that way you'll know to pay attention, because what you're learning today is going to come back and bite you in the butt if you don't learn it the proper way. All right. What about these OH groups, these nucleophiles? Before I talk about the SN2 or SN1s, I want to give you kind of a brief rundown of a chart. You're going to find this chart in your textbook, and it ranks things in order of prettiness. All right, so here's this chart. You can pause the video here and write down this if you want, or find it in your textbook if you want. This chart's always going to be given to you on a test. If you're doing the Blackboard assignments or the online homework sets, folks, I would at least have this chart handy because you're going to need it. This is really going to determine what is pretty and what is not. So this chart I don't want you to memorize. All right, that's silliness. I'm not into that. Okay, memorizing all of this kind of crap that you'll never use again. And you're probably thinking, well, I'll never use organic chemistry again. Well, I know that, but somebody at some point in time thought it was good for you to take the class at least. But this kind of information, I mean, this is stuff is learned and people know the ranking orders, but only after they are in organic for quite some time. And I just don't want you to take the time to memorize the chart when it will be available to you on the test. And make sure that you pull out this chart or that you find this chart when you do the homework assignments on the internet. All right. Okay, so that's where I'm going to stop this video. I'll come back to this chart. I'll explain this chart in the next video, how to read it, how to interpret it, what does it mean to us as far as reactions go. And then I'll show you more of a short-handed kind of version of a chart that takes some of this stuff out of there, and it just really focuses on the common groups that we're going to be seeing that these reactions will be using. So that's where I'll stop this video. In the next one, we'll pick up from here, and we'll keep on a trucking.